So, right, I'll be taking the day one for this AI bootcamp, 7-day AI bootcamp, and I'll be introducing all of you to LLMs and how context works in the context of LLMs. So, right, so let's go back to the advent of AI back in 1970s when we first discovered an architecture called multi-layer perceptrons or yeah, so multi-layer perceptrons are basically they're analogous to how neurons work in a human brain, and it was made um, it was made to streamline how how we're gonna get how we are gonna get computers to work with data instead of hard coding every single thing that we want the computer to do. So instead of working with algorithms, your traditional algorithms, we basically made it so that the computer can work with pre-existing data and learn how to use the data itself. So to start off, I'll just be sharing my screen. Just give me 1 second. I hope uh, you guys can see my screen. Is the screen sharing working?
Yes, it's audible,
Yeah.
visible.
All right. So starting off from our vanilla neural networks, basically these units, the circles, as you can see them, these circles, they are analogous to how neurons are in a human brain, and this is your traditional neural network, right? And this is basically a fully connected neural network in which each unit is connected to every other unit in the subsequent layer. So this right here, wait, one sec. So this right here is our layer one, and this right here is our layer one, and this is the other one is our the other one is our layer two. So right. So what we are doing basically, the first layer it's gonna handle feature extraction from whatever you feed into the input, and it's basically gonna take 4 neurons uh, and feed forward the um, I'm sorry. So right. So it's gonna take inputs and it's gonna send it off to the second layer, and at the end of it, what we will get basically is so for instance, if we have to classify whether something is true or false, and we have two mm, these two neurons, the ones I just made, they represent if something's true and false, then all right. So since it's a fully connected neural network, we're gonna make sorry, we're gonna make connections from each of these to the final output layer. And, right. So for instance, we have a bunch of inputs and we want to classify whether it's true or false, whether a certain attribute about the input is true or false. Then we're gonna send it off to the layer one, and then it's gonna go to the layer two, and then furthermore to the final layer, which is the output layer. It's gonna give us a probability distribution of it's gonna give us a probability distribution as to how much us as to how much the certain attribute is going to be true or false. The magnitude of it is going to be true or false. Uh, so these are our traditional neural networks. I'm not going to be delving too deep on them because we have a lot to cover. And this is all primitive technology, right? So we have come a really long way since then. So this is our traditional feed forward neural networks. For a traditional feed forward neural network to work, for a traditional feed forward neural network to work, we basically have to feed data sequentially. Oh, I'm sorry, guys. I just got a message from one of the authorities that I'll have to start from even more basic stuff. Okay, so I'll start with machine learning then. I'll explain how ML is and how deep learning and subsequently LLMs or generative AI, whatever you want to call it, they're derived from the domain of deep learning. All right, so machine learning is this big domain. Machine learning is this big domain that emphasizes on learning, on figuring out new stuff using using data instead of hard coding everything. For instance, we've always had algorithms like like Dijkstra's algorithm and A star search, right? If you guys have heard of it, and breadth first search, depth first search, or greedy's best first search. So all of these algorithms are basically hard coded in order to figure out something, um, in order to arrive at a deterministic solution to a certain problem. What machine learning does is you feed a lot of data, and the more data you have, and the higher quality data you have, the better your model will be. So yeah, so machine learning basically is a domain in CS which deals with data. And machine learning is grouped into a lot of subsets, and I'm not going to touch all of them, but we're going to see all of the relevant ones. So we have super, one sec. We have supervised learning. So supervised learning deals with modeling data that we have labels for, and then we have unsupervised learning. Sorry. We have unsupervised learning that basically, mhm. And then we also have reinforcement learning. So basically, supervised learning is data you have labels for, and unsupervised learning is data that you do not have labels for, and reinforcement learning is a category which deals with rewards. And what it does is basically based on what your model gives you, um, on the basis of data you provide to the model, what it returns is a certain reward function. And the goal of the model is to maximize the reward function, so as to minimize the loss incurred, right? So so these are all your traditional models, and then we also have deep learning. Okay, one second. We have deep learning, which is basically a subset of machine learning that deals with neural networks. So traditional machine learning, it does not use neural networks. All right. Traditional machine learning is just based on like you have supervised learning algorithms like k nearest neighbors and linear regression. I'm sure a lot of you must have heard of linear regression. And then supervised learning, may we have unsupervised learning. Maybe have uh, unsupervised learning. We have just one sec. I'm sorry. Yeah, all right. Sorry. So I was at unsupervised learning. Yeah. So unsupervised learning, maybe have something like k-means clustering, and in reinforcement learning we have Q star. So anyway, so moving on to deep learning. Deep learning is further. It deals with neural networks, and it's further um, classified into. Deep learning is further classified into various types of neural networks, right? Convolutional neural networks, as you must have heard of, and what recurrent neural networks. Yeah. Did anyone say something? Never mind. Right. So in deep learning, um, we have various types of neural networks. The convolutional neural networks, recurrent neural networks, and uh, the most the most latest the most latest advancement that we have in deep learning are transformers, which power our modern day AI, which are responsible for the boon in modern day AI. And so, right, so I was explaining you neural networks for deep learning. We are coming back to neural networks for deep learning. So what I was explaining before, this is all deep learning. This is a neural network, your traditional feedforward neural network. What this does is takes data sequentially and feeds it into the input, and these middle layers are called hidden layers. What we are concerned as users are just the input and output, because all right, so what neural networks essentially are a function that map an input. They are functions that map input to an output. We as users are only concerned with the input and output, right? So this is the input layer. This right here is the input layer, and the rightmost layer is the output layer. Um, so this is the output layer. So what a neural network basically is basically it's just a function that maps an input to an output. What you feed. So for instance, you enter a prompt in ChatGPT or Claude or anything. What it does is basically is just a function that maps it to an output, right? But all these layers in between, these are hidden layers. Like these layers in between, these are hidden layers, and there can be multiple of these in between. But again, so all right, so moving for we are right now only in the realm of like vanilla neural networks, like very traditional classic neural networks. For these to work, for this classic neural network to work, we need to have the data in um, in the exact length as the input layer neurons. For instance, if I have four words, like if I have four words, she, she was, She was a um, nurse, right? So these are our inputs right now. And what we are doing in this neural network is basically classifying whether this is true or false, right? But what if the input that we have exceeds the length of these neurons that we have? What if we have another? What if we have another sentence like the boat landed on a riverbank? Now that's not four letters, right? So we are exceeding the number of neurons. So this is where these traditional neural networks start failing. They cannot handle recurrence. They cannot handle inputs of varying lengths, right? So this thing this thing only works. These neural networks only work when we have a specified length. When we have a specified oh, I'm sorry. When we have a spec okay. um I don't know why it's not working, guys. I'm so sorry. Yeah. So when we have this, just give me a second, guys. I'm sorry. All right. When we have a specified length for the input, right. Now, to deal with these limitations, what we discovered were recurrent neural networks. So I'll use these. So what recurrent neural networks do? I'll just draw this out. So recurrent neural networks, what they do is they take inputs and inputs go into the model. The model generates output and output. The model generates an output. Now, what happens in the recurrent neural networks? The model takes the output again. The model and what the model has learned again, and it uses it leverages this as the next input. It leverages this as the next input for the next token, for the next token in the network. And then this keeps on cycling. The input gives it to the model again. And this again goes to the output. And it keeps leveraging this to get the output again and again. And similarly, these recurrent neural networks, they can map like a varying length of input to a fixed length of output, as well as a fixed length of input to a varying length of output, and a varying length of input to a varying length of output. So, you guys have some questions after now. I'll have to allow you. Does anyone have questions? No. Right. I'll read that as well. Right. So this is where rectangular notebooks come in handy. But now what happens is that rectangular notebooks also have this limitation. The fact that the data is being handled sequentially, right? For instance, if I input something like right, so like the dog is barking. If we have this sentence. Now, what the RNN or rectangular is doing, it's taking the input, it's taking the first word as the first input and giving it a model. The model generates the output. Uh, so yeah, as I was first you guys see what wondering why do you give something like the dog is barking to a model just like that. For instance, you have a story or let's say you instead of this, take a more comprehensive example. For instance, you have you ask the model to complete a story that starts like this: once upon a time. Right? Once upon a time. You give your model this, and you ask it to complete the story for you. Now, when it is before 2017, okay. The keyword here is 2017 and regular environment. So before 2017, what happened? What used to happen? That these not large language models, they used to take the first word as the input, give it to the model. The model produces an output with it. I'm sorry. Yeah, the model takes this as the input. Then the model takes what it has learned and it uses that as the next input. It doesn't produce the output in this case. Right? There can be multiple different architectures for an RNN. In this case, the architecture would be something like they take the model takes the first word of the input. It gives it feeds it to itself and it maps it to the next input. Then also it acts as the input for the next iteration and it gives it back to the model again. And similarly, all of these words, well, all of these words are finally, all of these words have been fed to the neural network. The model basically makes a context-rich mapping for the entire for these four words. It makes a context-rich mapping for these four words, and then it starts to produce the output. All right, then the model. Let me just type this in. I'm writing my D2 legible. Model takes this as the input for the last time and it starts producing the output. Now for the output again, for the output, what happens is for the output, it produces a first token. Like once upon a time, let's say it starts giving us a probability distribution of what the next most likely word is going to be. So once upon a time, a lion fought a tiger. All right, very random, I know, but yeah, it is what we're gonna have right now. So output. So okay, so next likely word. Let's say its next most likely word that it generates as output is uh, uh um that will be uh and then it gives it to then it feeds it into the then it feeds this output into the model again to give as the input it feeds this output as the input for the model again. Yeah. as the input for the model again, to give us the probability distribution for the next most likelihood that the model is going to predict for us. So let's say that next most likelihood is a lion. So this is gonna keep happening until we get a desired result, right? So this is an RNN. All right. This is a recurrent neural network. But the limitation for this is this operation cannot be parallelized. All right, we'll have to wait for the model to first process once, then upon, then time, then even this comma. All right, even this comma. This also counts as a token. Right. So token also reminds me. I think I moved pretty fast again. What these are, these individual characters, all of these are tokens. These are all tokens. And these are going to be very important when I start explaining you guys what context size is for an LLM, for a LLM. Sorry. Yeah. So these are all tokens. What a LLM does is break down all of your inputs into a set of tokens. And all of these tokens, what happens is, for instance, this once once has a vector mapping. It's mapped as a vector inside of a LLM. It's mapped as a vector. Okay, this is basically a vector inside inside a LLM. Once upon time. These are all vectors inside an LLM. For us humans, for us to process natural language, obviously we'll feed it as natural language to the large language model. But what the large language model underneath, under the hood, how it is processing all of these words is as a vector. Okay, so these are all this once upon time. These are all vectors underneath, and all LLMs have basically a lookup table, which is, to be fair, this lookup table term that I'm using, uh, it's a very layman's term to refer to it because it's actually called an embedding matrix. No, I'm sorry. One sec. So this lookup table is called an embedding matrix. And for most large language models these days, the embedding matrix contains around 50K to anywhere between 50K to 100,000 tokens, right? For each of these, for even the comma, right? Even if you have a bracket, even an individual comma and an opening bracket, these are all individual tokens, and they all have vector mappings inside of this embedding matrix. The embedding matrix is basically a list. Sorry, it's basically matrix that contains a mapping for every concept, for every. I don't think my writing is going to compensate. Uh, anyway, so yeah, so this basically contains the list of all vectors, the lookup table or the embedding matrix. This contains a list of all the vectors that the LLM is going to use to refer to all of these tokens individually. Okay. So I've touched tokenization. I've touched RNNs. All right. Now we can start delving into transformers, or what powers our modern day AI. What basically led to the boom, the modern day boom of AI. Anyway, so in 2017, what happened? A bunch of researchers at Google DeepMind They wrote a paper called Attention. It's called Attention. Wait, I think the text is too small. Mhm. Attention is all you need. So this is the research paper. You guys can refer to this research paper if you want. You can find it very easily. Um, so this was made by a group of Google DeepMind researchers, and what happened? They introduced this new architecture called a transformer. Right. So, firstly, I hope that you guys know what the full form of GPT is, right? Your chat GPT that you use every day. The full form for GPT is generative. It's it's generative pre-trained transformer. All right. So in this case, I am generative is pretty self-explanatory. Pre-trained. Pre-trained means the pre-training is a procedure how the transformer adjusts its weight uh, in order to produce outputs, and transformer is the actual architecture of the LLM. So transformers, right? So we, referring back to RNNs, the limitations of RNNs were that the data is being fed sequentially, one word at a time. Now, thus it cannot be parallelized, right? RNNs RNNs operations cannot be parallelized. But just think, what if we could parallelize all the input tokens? For instance, what if we could feed she? Oh, I'm sorry. What if we could feed she was a nurse? All of this in parallel to a neural network. All of this in parallel to a neural network. But how would we do that? Because for instance, if we have a word called, for instance, I'll take the classic bank example. Bank by itself does not have any context to it. It can either mean a river bank or a financial institution, right? So if I add to it the word river bank, or to give you a more fair example, what if I say that the boat la- mm, landed on the bank? In this case, you can tell it refers to a riverbank, right? It's not a financial institution in this case. So the context in this case is very, very important. To process natural language, context is very, very important. So by these words by itself, she, was, a nurse, these tokens by itself, they don't mean anything. The was does not mean anything by itself. But if I give you this entire sentence in one go, how will we how will we get a context rich meaning out of it? So in order to do this, what these researchers did basically, they introduced a mechanism called attention, the attention mechanism. So attention mechanism, it works in the same way as we do when we're processing information, right? So if you watch an entire movie in one go, obviously there are going to be some parts that you pay more attention to in order to understand its plot, right? And what if all right, so I'm giving you a lecture here, right? I'm giving you a speech, a lecture. I'm a speaker here. So in everything I say, there might have been some parts of it that you guys paid more attention to, right? So this attention mechanism works in a similar manner. What happens is when we are feeding, when we're feeding these tokens individually, these she, was, all of these tokens individually, when you're feeding all of these individually, what happens is that the attention mechanism, it basically these words communicate with each other. So remember, that hmm, I told you guys that all of these individual tokens, they're all vectors inside a LLM. So all of these vectors for each word, each token, they communicate with each other, and they change each other's values. For instance, if I have a vector here and a1, a2, a3. Actually, let me declare real values. All right. So if we have something like minus 2.3, 2.5, 3, minus 3, and let's say this is the encoding for she. Mind you guys, in modern day LLMs, this size, this is as long, this size can as this size of these vectors, they can go as long as something like 40K dimensions. All right. I have taken three just for this, just to make you guys understand. But the dimensions of these vectors inside an actual LLM, they can go as far as up to 40K or something. To give you an example, GPT-3 had had a vector mapping for as large as I think 13,000 tokens. Sorry, 13,000 dimensions for each vector. Anyway, moving on. So and then we have a mapping for walls. So this is she. This is the mapping for she, and this is was. Excuse my handwriting. Let's say this is 5.16 and minus 1.1. Right. So what attention is basically going to do? It's going to let these two vectors communicate with each other, and what and how the communication is going to work. It uses something called key query and value matrices, and I'm not going to touch those right now. They are too far beyond the scope of this lesson. But anyway, so they change they change the mappings of these vectors. Uh, Something like 2 gets changed to minus 2.6, let's say. And similarly, all of these mappings get changed for all the tokens. Let's say this becomes 5.6 and so on. So the attention mechanism basically grants the attention mechanism basically grants all of these individual vectors a context-rich meaning such that the LLM can take all of these and give us outputs, right? Give us meaningful outputs to be precise. So this is where the concept of a context comes in. How many of these tokens? How many of these tokens uh, an LLM is going to look at the same time in order to process information? All right, these are all your tokens. Now, I've only taken 4 tokens right now, but you guys must be aware that for all of you, ChatGPT or Claude or anything. Yeah. Did anyone say something? Right, never mind. I thought I heard something. So anyway, so these individual tokens, where was I? Just one second. Right. So context. So what happens that these? individual tokens. I've only taken four tokens right now. She was in hers, but yeah. So all of you who use Claude, ChatGPT, Gemini, etc., you guys must be giving, I don't know, maybe 2K, 3K tokens easily for one prompt if you really want to get something meaningful out of it, meaningful out of your conversation with the chatbot. So this thing, this is the context. This can be the context size. Like, this is the context. Just one sec. This is not actually the context size. I'm sorry. I what this is the number of tokens that you may normally feed to ChatGPT, Gemini, or something. Now, if I take example of GPT-3, all right, GPT-3 had a context size of 4096 tokens, or how it's referred to in recent terms, it's basically a 4K context window. This is a 4K context window, right? So, and we have come a long way since here. For instance, right now, Gemini 2.5 Pro. Let me quickly write Gemini 2.5 Pro has a mind-boggling context size of 1 million tokens. GPT-3 is primitive. Like you guys can see that we have come a really long way since GPT-3. Uh, Also, I may be wrong about this GPT-3 token size because, as far as I remember, it's either 2048 or it's 4096. I'm not sure if it's 2K or 4K. You guys feel free to correct me on this one, but it's either 2K or it's 4K context window for GPT-3. It has to be one of those two. So, anyway, moving on to Gemini 2.5 Pro. And also, to give you context size of another popular LLM, Claude, which some of the coders might use. Claude has a context window, 3.7 Sonnet. 3.7 Sonnet has a context window of 200K tokens. Right. So Claude has a this is 3.7, by the way, not 4. Okay, the 4 that just came out a few days ago. This is not for 4. This is Claude 3.7 Sonnet. Yeah. So this is the context size for popular LLMs, and this basically refers to the number of tokens the LLM is going to look at simultaneously in order to process the input. Okay, so coming back to attention mechanism and context size, what it does, so this attention mechanism, it gives the attention mechanism, it gives us it lets these vectors all talk to each other, and I'm saying all of these vectors. Okay, I just put two here for ease, for the sake of ease. But all of these inputs that you feed into it, the vectors for all of the input tokens, they're all going to talk to each other, all of them. This is going to talk to this is going to talk to this, and this as well. Although this is not necessary that it's going to talk to each and every one of the tokens individually, because this is just done in case this is like the most traditional form of attention mechanism. This is just done in order to make um, the input more what do you call it, foolproof, right? So that the LLM does not hallucinate. Okay, this is called a full attention. Full attention is done in order to prevent LLMs from hallucinating. Hallucinating is, you must have noticed that sometimes you asked you ask a LLM to do something for you, and it starts assuming and creating some random data out of nowhere that you didn't give it, but it does that regardless. That phenomenon is called hallucination in LLMs in the context of AI. So yeah, this is full attention. This is done in order to decrease the chances of a LLM from hallucinating. There's also things like sparse attention, in which the transformer is only going to pay attention. The inputs are only going to pay attention to the more important embeddings. Okay. For instance, this is going to talk to answer. This is going to talk to this one. This is only going to talk to this one, and this one is only going to talk to this one. So selective attention or sparse attention. That it's basically what it does is prioritizes the more important stuff to make the operation more efficient. And one more thing, in LLMs, the context size the context size is proportional to the square of the computation required to compute attention. Okay, computation for attention. It's proportional to the square of the computation required for attention. So you guys must be able to deduce that increasing context from something like 4K, 2K to something like 200K. You guys can imagine how much more computationally demanding this thing must be, right? How much computationally demanding this upgrading the context size must be. So when you are increasing the context size from 2K or 4K to 200K, the computation exponentially increases, quadruply increases. Uh, okay, so you have to be careful while handling all of this stuff when you're uh, working with LLMs, right? Uh, so that's context for now, and coming back to transformers. Transformers have this embedding matrix, right? The embedding matrix. What it does, you have taken an input. Was she is a nurse, and sorry, you have taken she's a nurse here, and uh, I'm sorry. So now what the transformer does is it's going to use the embedding matrix to get vector embeddings for for each of these tokens, right? And then maybe you ask your LLM to complete this story, this sentence. Okay, you ask the LLM to complete the sentence. She's a nurse dash. Okay, so you ask the LLM to complete the sentence or add one more sentence after this one. So what your LLM will do basically, it will take the embedding matrix. Okay, the embedding, proceed to attention layer. This is called this. The first thing is going to be your attention layer, and then it's going to go to a feed forward neural network layer. Okay, or a multi layer. perceptron layer, MLP for short. Uh, Wait, I'll just write down multi-layer perceptron for you guys so that there may be no confusions regarding the spelling. So this is a multi-layer perceptron layer. Actually, let me write this horizontally because it might be confusing for you guys. Right. So mm, this is your embedding. This is your embedding matrix that gives you all the tokens, and then you give it to the attention block. Keep in mind, this is a self-attention block. Okay, this is called a self-attention, and I'll tell you why in a bit. Self-attention. This goes to a multi-layer perceptron block, MLP for short. Multi-layer perceptron. And then there's a batch normalization layer in between, but I'm not gonna. There's one batch normalization layer. Okay, there's one batch normalization, but I'm not gonna talk about it for now because it's really not worth getting into right now. Right. So yeah, so batch normalization after every layer of attention and MLP. Okay, batch normalization. Then again attention, another layer of attention, self attention, another layer of MLP, and another layer of batch normalization, then another layer of attention, MLP, and so on. This goes on until however long you want, right? Until however many attention layers and multi-layer perceptron layers you want. And so I already told you what the attention block does, right? It basically allows the vectors to communicate with each other and give each of the vectors a more context rich meaning in order to process input. Now the MLP multi-layer perceptron layer, what it does in this layer, the vectors individually, they don't talk to each other. The talking to each other part is only is handled by the attention block. The MLP block handles handles like storing facts, information, all of that stuff. And it's actually much more complicated than that, but I'm not going to touch NLP for now into detail because I think we need to stick to the scope of this lesson. So attention, MLP, and then however many layers of this you want. For your reference, GPT-3 had 96 layers of all of 96 layers of this attention, MLP, and then a batch normalization layer. It had 96 layers of all of this, subsequent layers of all of this. And what at the end of all of this, at the end of all of this, what it does in the final layer, just before batch normalization, what it does after all this 96 layers, you have a huge matrix. Okay, let's say B, C, D, E, F, G, H, I, J, K, L. Okay, so what it does, excuse my handwriting by the way, I'm so sorry. So what happens in the last post MLP after the last MLP layer, the LLM takes this final vector embedding, this final column, which has now absorbed all the context-rich meaning from outside of its, from all of from all of the words around it, from all of the tokens around it. For instance, you fed it, she was a nurse, right? You fed the model, she was a nurse. So keep in mind, this does not directly refer this vector does not refer to the nose directly. Okay, I've just written it for the sake of understanding. But anyway, so what it does, it takes the last column, it normalizes it using something called a softmax. Okay, it it normalizes it. It's something using softmax, and this gives us this softmax basically returns us a probability distribution. Okay, this returns us a probability distribution for the next most likely word. For instance, it's the, why, what. For instance, let's say these are the next most likely words that we're gonna have after the softmax normalizes the probability distribution. Okay, and what it does for let's say that um, let's say this is what, and this has the highest probability, right? So it's gonna take this and it's gonna map it to, let's say, I don't know, 35%. This is 30%, and all of these get certain values too, and all of these add up to 100 for obvious reasons. That's what softmax does. What basically happens, all of LLMs, okay, all of LLMs that I've discussed so far, literally every single operation inside LLM, they're all just matrix operations. It's all just matrix multiplications. Everything inside an LLM is just matrix multiplication. So after all of these matrix operations, no, this last this last column, it basically gives you values like it will basically give you values like, let's say, 35.3 minus 67.9 or minus 57.4. Let's say it gives you these values. All right, for the vector embedding. What we have done and what we have done using softmax is we have normalized this. We have normalized all of these values to give us values between 0 and 1. Okay, between 0 and 1. For instance, this becomes 0.2, this becomes 0.5, this becomes 0.3. Okay, what what softmax here did for us is it normalized all these values such that all values are between 0 and 1, and all of these values also add up to 1. Okay, all of these values also add up to 1. So this is what softmax has done for us, so that we can create a probability distribution for it, and we can hence predict the next most likely word. Now you guys must also be wondering that um, okay, I have this probability distribution for the next most likely word. Now, you guys must be wondering that every time you feed something into the neural network, into LLM, it gives you a different response each time, even for the same prompt. For instance, if I just give a LLM, she is a nurse, 2 times in a row, I'm gonna get and I'm gonna ask it to complete the story. Right, I'm gonna ask it to complete this story. I'm gonna get a different story each time. Right, you all must know it if you have used LLMs, like really used LLMs. You get a different story. Why does that happen? Because shouldn't it be like the highest probability should be deterministic or consistent? You guys must be wondering that this should be consistent. Actually, the model the model is deterministic. Okay, these LLMs are deterministic, but what it does, what an LLM does, it introduces the concept of softmax, softmax with temperature, temperature. Um, sorry. So softmax with temperature. So what softmax with this new entity that we've introduced, temperature, what it does is, so the higher the temperature is, okay, the higher the temperature is, the more closer, the more closer and the more normalized, like let's say this is higher, the higher the temperature is, the more closer the probability distribution is going to be. For instance, you can see that there is a very small, there's a very minuscule difference between the magnitudes for all of these all of these probabilities, right? And that is because we have taken a high value for temperature here. And when you take a lower value for temperature, what happens is the LLM starts prioritizing. It starts giving the most likely next word a more higher magnitude compared to the rest of the words. So let's say this is the most likely word. What lower temperature did is it just gave this most the highest probability uh, in the probability distribution. So when we have so when we have like so we don't want the LLM to generate the same response every time for the same prompt because of various reasons. Like you want something unique out of us to like you if you ask LLM to generate a story, you want something unique every time, right? So for similar reasons for other stuff as well, you don't want the LLM to give you the same output every time. And so that's why this temperature thing exists. And what it does now the LLM randomly selects, for instance, let's say this value has the highest probability in this case. But what the LLM will do now, it will randomly select some other probability that is close to it, but not too far from it. Okay, it's going to be close to it, but not too far from it, in order to give us still a very consistent. It's going to still give us a consistent. Sorry, it's still going to give us a deterministic answer to the problem, but uh, it's still going to give us a deterministic answer to the problem, but it's not going to be exactly using the same words. Okay, so right, so that's temperature. And also, if I bring the temperature down to zero, what happens? The other most likely words, all of them get a zero probability, 0% probability, and the most likely word gets 100% probability. So you don't want that. Okay, you never want your temperature to be zero. That's a bad practice. If you guys, I think you might be using APIs for ChatGPT or Claude or whatever later on in this bootcamp, but and you will have the ability to change temperature for each prompt that you give it. Please don't ever set it to zero because it's only going to give you the same answer every single time. So yeah, so that's temperature. So the model is still deterministic, but it does not give you this exactly same answer every time. Right. So that's attention and transformers, how transformers work. I have still not touched a lot of very crucial topics, I would say, but I've covered everything nonetheless. And you guys now understand how important context is and the context of LLMs, right? And yeah, that's it. Any questions so far? Does anyone want to ask anything? I think I might have rambled on too long uh, without making the session more interactive. If you guys have any questions, feel free to ask me.
Guys, please, if you have any doubts, you can ask right away. because all these topics taught here will be very important for the upcoming lessons as well and for the project that you'll be making. All the context part is very important for the projects. So if you have any doubts, that will be cleared right away. You can just put it in the chat as well if you don't want to speak.
And let me see the chat once.
No doubts.
GPT-3 has a 2048 token. Yeah, I said so. I wasn't sure about it being 4K or 2K, but yes, it's 2K, I guess.
I suppose no one has any doubts. I think Siddharth, you can just get over with the module as well, like Microsoft Learn module for the batch.
Uh, just give me 1 second then.
I'll share the link in the chat if you need that.
Yeah, just give me 1 second. Mm,
All right. Because it's on the website as well, I'm putting the link here as well.
Abhishek, can you check your WhatsApp for once?
Yeah, I have shared in the chat of the meet. You can check that.
Oh, all right.
Yeah. Guys, this is a module like Siddharth will be going along with this. And you can just easily get a badge from Microsoft Learn that will be added to your profiles as well. Yeah, Siddharth, over to you.
So, right. Mhm. All right. So, uh, in the Microsoft link that Abhishek had just shared in the chat, I have already explained you how LLMs work underneath a very high level explanation and abstracted, but right. So, um, what you'll be doing is going through all of these modules, like understand LLMs, and there's also core concepts of LLMs and when to use LLMs. Uh, right, and then there's also this which model to use depending on your use case. For instance, they they recommended uh,
Siddharth, I think your
like
screen is
yeah,
not fully shared. It's the whiteboard that is being shared.
yeah, I wasn't. Oh, all right. You want me to? Okay, never mind.
I was thinking that would be a better way.
All right.
Yeah.
Yeah. So first we'll be going through first. I've already explained you understanding LLMs, right? Uh, so this is I've already told you difference between traditional natural language processing. That was basically I told you about how AI was before the advent of transformers like RNNs, and uh, we also had grammatical rules like grammar rules, contextual grammars, and all. That was traditional language natural language processing, and now I've explained to LLMs the attention mechanism and everything. Right. So this goes over the understanding of LLMs. Then we have core concepts of LLMs. I've told you tokens. Tokens are uh, the vector embeddings. So the tokens are the individual leximes in your input string, and they've just given you examples for like what tokens are and how does completion work in the context of LLMs. And then we also have again when to use LLMs. So you have you can have multiple use cases for it. You can make your LLMs write code as well, which I'm sure a lot of you must do, and I do as well. And so text processing obviously, and you can also use LLMs for image generation. Now you have DALI and you have Gemini. Gemini also has a pretty good image generator for those of you who might not know, and it's free. Right. And then we have which model to use in which case. So it gives you all of these references for GB35 Turbo, GB35 Turbo 16K, which basically is giving you 16K tokens, and GPT-4 32K, again 32K tokens now in this case. So, right. And DALI, obviously, the go-to diffusion model for image generation, and also, yeah, and then you have your module assessment and all, which you can use to check your how much you've understood about LLMs, right? And yeah, that's all. That's it. Then the summary, and then you're done. That's all. Or do you want to take over, Abhishek?
That was all for the session, guys. As soon as you complete the assessment there, you will get a badge from Microsoft Learn. And if you have any doubts regarding anything taught, you can feel free to ask Siddharth, because these topics are very important for the upcoming sessions and your projects.